welcome to A's Online. Today we are going to discuss about the revision of signals and systems. So before that, we have this offer. It's a 20% off. Use this code PONG Pongal 20. This is applicable on 10th and 11th January 2025. So this is applicable for classroom coaching, recorded courses and online live classes. So signals and systems for electrical engineering. So what's the weightage? You all know you have completed the course. You would have practiced many problems. You would have solved by now 2023, 2024 papers. You can see 10 to 11 marks from this subject. (10 to 11 marks from this subject. So what are the topics that need to be covered? So let's start. I hope you have this idea now. Let's start with a revision. Properties. So before these properties, I want to discuss one interesting thing. This is really important. If x of t is real, then you see this C minus n will be equal to Cn conjugate. This is very important, students. What will be C minus n? It is simply Cn conjugate. So find Cn. C minus n can be easily calculated through a conjugate operation. Once you know C minus n, if you know Cn and C minus n, look, An can be calculated, Bn can be calculated, every other detail can be easily calculated. So most of the time real periodic signals would be given. Very rarely they will put a complex periodic signal. Is this important? Yes, very important relation. So with this we'll move on to the properties. Very important section. So the first one is a time shift property. What does this time shift property say? If x of t is a periodic signal whose Fourier series coefficient is Cn, then the Fourier series coefficient of x of t minus t naught is e power minus j n omega naught t naught into Cn. This is called the time shift property. X of t minus t naught Fourier series coefficient is e power minus j n omega naught t naught into Cn. So let's see the frequency shift property. If x of t Fourier series coefficient is Cn, then which periodic signal coefficient is C n minus m? And the answer is, it is e power j m omega naught t into x of t. So the Fourier series coefficient of this signal, that is e power j m omega naught t into x of t, the Fourier series coefficient of this is C n minus m. So if there is a shift in the frequency domain, there you will see a exponential term in the time. If there is a shift in the time domain, you will see a exponential term in the frequency domain. We have been highlighting this, giving you the taglines in the classroom. There are many other properties. Let's learn differentiation property, time differentiation. So what does this say? If x of t Fourier series coefficient is Cn, then d by dt of x of t, the derivative of x of t is also a periodic signal whose Fourier series coefficient is Jn omega naught into Cn. If you have a second derivative, then it will be like Jn omega naught whole square into Cn. Jn omega naught whole square into Cn. You can expect questions from these properties, students. There are few more properties. Let me highlight them. Let me put all of them at one place for your reference. Before or while writing full length mock exams, because this is the time where you people write full length mock exams, if you can revise these things, this will definitely help you in getting more marks. There are few more properties, so let me write them at one place. There is a property called time scaling. According to this time scaling, if x of t Fourier series coefficient is Cn, then x of a t Fourier series coefficient is also Cn. So here the time period is t, the angular frequency is omega naught, whereas here the time period is t by a and the angular frequency is a omega naught. But the Fourier series coefficients are unchanged. This was asked multiple times in your examination. X of a t Fourier series coefficient is Cn, but the time period is changed and the angular frequency, the fundamental angular frequency is changed. Next, so there was a student who asked, sir, how do we find the energy and the power when something is given in the frequency domain? So for him, look at the answer, student. There is a theorem called Parseval's theorem. So what Parseval's theorem says is, this is the expression for average power, it is 1 by t integral over t x of t modulus square dt. This is the expression to find the average power in the time domain. The Parseval's theorem says, okay, you can either use this, or if you know the Fourier series coefficients, then do this. N from minus infinity to infinity, it is Cn magnitude square. You take the magnitude of all the complex exponential Fourier series coefficients, you square them, add it, that gives you the average power. So earlier there was a student who asked this question. This is how you do it. Then how do you find in Fourier transforms? Again, there is a Parseval's theorem in the Fourier transforms. I will discuss the Parseval's theorem in Fourier transforms as well. These are the properties, students. In the past GATE examinations, there were questions on these properties. So you are supposed to remember them instantly. And let me add one more point here. So when it comes to the Parseval's theorem, this is how you do it using Cn, but you can also use A and Bn. So how do you use A and Bn? I'll tell you. It is A naught square plus half summation n from 1 to infinity. It is An square plus Bn square. The power, the average power can also be calculated using a relation like this. So on a single page, I have all these properties which are really important for you. Before the exam, before your full length mock exams, if you want to revise, you have to revise it this way. What students might feel is, with this short notes, we revise, we get the ranks. No. You know who is going to get the ranks? The ones who retry this instantly in the exam. The ones who know how to apply these and then solve the numericals. The skill lies in solving. So those students are going to get. Those who keep writing mock exams every day, for them on the actual exam day, it's like a mock exam only. They don't have any tension, they just go and write it. For periodic square wave, Cn is proportional, or you can write Cn is inversely proportional to n. This is a very important note point. So usually square waves show half wave symmetry. So even harmonics vanish. Whatever relation I am saying, this is valid for odd values of n. So where n is odd number, because for even numbers Cn is it is 0. So there is no discussion about even coefficients. Do you people remember the Dirichlet conditions, students? Let me highlight Dirichlet conditions. theoretical questions were asked from Dirichlet conditions, you know. So every periodic signal may not have a proper or a valid Fourier series representation. So who has got the valid Fourier series representation means the periodic signals who are absolutely integrable in one time period. So x of t must be absolutely integrable in one time period. The second condition is that x of t must have finite number of maxima. It should have finite number of maxima and minima. It should have finite number of maximas and minimas in one period. The third one is x of t must have finite number of finite discontinuities. In one time period. So based on this, some theoretical questions have appeared in the examination. I have discussed what kind of theoretical questions have appeared, and when you have a discontinuity, a finite discontinuity, I also said the Fourier series value will converge to the average value. So that is also important. So this completes a quick recap of what are important things in Fourier series. So what happens in CTFS, I tell you. In CTFS, in the time domain, this is time domain versus the frequency domain. In the time domain, the signal is continuous. So in the frequency domain, whenever you draw Cn or the magnitude plot or the phase plot, it shows aperiodic nature. In the time domain, students, it is periodic. So when you look at the Fourier series coefficients, they are discrete in nature. So this can be asked in your examination. I'll quickly write what happens in the various cases. This is for CTFS. Will you be answering for various cases? Let's see. Will you answer for DTFS? So in DTFS again you write time domain, and here you write frequency domain. So in DTFS, in the time domain, it is discrete. Discrete in one domain leads to periodic nature. Discrete in one domain leads to periodic nature, meaning by you will also have a Fourier series coefficients there, but the Fourier series coefficients show the periodic nature. This is really interesting. And it is also periodic in time. Now when it is periodic in time, you remember this, I mapped something like this. Where is that? If it is periodic in one domain, then it shows discrete nature in the other domain. So come on, try to answer this. Periodic in this means it is discrete. So this is something where in the time domain you have a discrete and periodic nature. In the frequency domain also you have discrete and periodic nature. This chapter is called DTFS, which we haven't discussed so far. In 2022 and 2023, this was introduced after the COVID. In 2022 and 2023, they asked questions from this topic for electrical engineering. These questions look similar to that of these questions, but in the time domain it is discrete and periodic. In the frequency domain also it is discrete and periodic. So let's see what happens in CT-FT, which we call as Fourier transforms, CT-FT. So in the time domain, what happens? In the frequency domain, what happens? In the time domain, it's a continuous signal. So we know if it is continuous in one domain, this leads to aperiodic nature. So when you look at the spectra, the magnitude spectra is aperiodic in nature. It is continuous and aperiodic in the time. Aperiodic in the time leads to continuous nature in the frequency domain. So this comes under CT-FT, which is one of the most important topics we have. This is the next topic that we have to revise. And the last topic would be DT-FT. So what's happening in time? What's happening in frequency? The name itself says discrete time. So in the time it is discrete. If it is discrete in one domain, then in the other domain it is periodic. It is aperiodic in time. So due to this aperiodicness, in the frequency it shows continuous. It's a continuous function in the frequency domain. So this is about DT-FT, students. If you can understand this, if you can instantly retrieve this, if you can understand properties of all this, you can easily score in the exam. I'll give you a half minute, please go through this. So let's proceed to the next chapter, which is Fourier transforms. This is interesting. Lot of things are involved here. So how do you find the Fourier transform? The Fourier transform is calculated like this: integration minus infinity to infinity, it is x of t e power minus j omega t dt. If they provide you x of t, you substitute in this, you will get the Fourier transform. How is the inverse Fourier transform defined? You can also write x of t, which is 1 by 2 pi. This 1 by 2 pi always irritates all. So it is 1 by 2 pi integral, it is x of j omega e power j omega t, and then d omega. These two fellows are called Fourier transform pairs. We call the first one as the Fourier transform of x of t. Okay, so you should know these definitions. I'll write the standard Fourier transforms first. E power minus at into u of t, it is 1 by a plus j omega. E power at u of minus t, it is 1 by a minus j omega. E power minus a mod t, whose Fourier transform is 2a by a square plus omega square. You have e power minus at u of t minus e power at u of minus t, whose Fourier transform, if you want, you can subtract them. If I subtract them, a minus j omega minus a minus j omega, so it will be like minus 2j omega by a square plus omega square. It's like I also don't remember. I just subtracted this and then simplified. I got minus 2j omega by omega a square plus omega square as the answer. This is one set that you have to remember. There are many such things which I will give you one by one. Del of t, we will start with del of t, simple one. Del of t Fourier transform is 1, u of t Fourier transform is 1 by j omega plus pi del of omega. Signum function Fourier transform is 2 by j omega. So there are many such standard things, students. We will learn them one by one. If you have 1, then its Fourier transform is 2 pi del of omega. Let us learn about sine omega naught t, whose Fourier transform is pi by j del of omega minus omega naught minus del of omega plus omega naught. This is very useful. You have to memorize all these formulas. Cos omega naught t Fourier transform is like pi times del of omega minus omega naught plus del of omega plus omega naught. There are few more. I will help you with those. There is a Gaussian pulse. Hope you remember it. The Fourier transform of a Gaussian pulse is again a Gaussian pulse. Let us include that here. The Fourier transform of a Gaussian pulse is again a Gaussian pulse. The Gaussian pulse will look like this, e power minus pi t square, where in the classrooms we teach like the Fourier transform is minus pi f square, but if you can get it in omega, it would be useful. So in the omega, it's like e power minus omega square by 4 pi. So they might ask you questions on this standard transforms. They might link with the properties, anything can be expected. But I can tell you, at least one question you will get from Fourier transforms, that is 100% guarantee. Do you people remember this? This is minus t by 2, this is t by 2, let us say this is A. The Fourier transform is area, that is AT, sinc. I hope you remember this. It is sinc omega into, so the width of the rectangle, which is t by 2 pi. So area of the rectangle, sinc omega into width of the rectangle, the width is t by 2 pi. Students, sometimes they also ask you in F domain. So do you have the answer for the F domain? Let us see. Do you people have the answer for the F domain? The same thing can be written in F domain like this, AT. We all know omega by 2 pi is F. We all know omega by 2 pi is F. So you can say AT, it is sinc F into capital T. So these things are really important. The questions on rect, triangular are frequently asked. So let me show you for triangle. Let us say this is minus t, this is t, let us say this is A. If you have a triangular pulse in the time, then it is area of the triangle, which is AT, and then you have this sinc square omega into this width by 4 pi. This is 2t, students, by 4 pi. 2t by 4 pi is t by 2 pi. So this is again omega t by 2 pi. If you want to write this in F domain, it is AT sinc square F into capital T, because they also ask you in F domain sometimes. Majority of the time it is asked in omega, but they can also ask you in F domain. This is one more interesting question of the standard Fourier transforms, and the last one in this category, which is sin AT by pi t. You would have used this many number of times in your classes. The Fourier transform of this is simply a rectangle from minus a to a with a height 1. It's a rectangle, and this is in which domain? This is in omega domain. I'll give you a minute time. Please go through this. These are the most important Fourier transforms. Next, the properties. So, x of t minus t naught Fourier transform will be e power minus j omega, it's not omega not, omega, e power minus j omega t naught into x of omega. This is called time shift property. E power j omega naught t Fourier transform will be like x of omega minus omega naught. So this suggests that if there is a shift in the frequency, there is an exponential in the time. Okay, so I have to add one more quantity here. E power j omega naught t into what? X of t. Into what? X of t. This comes under time shift, this comes under frequency shift. So let's discuss one by one. It would be good if I write the names. This is called time shift. This is called frequency shift. If you extend a frequency shift, there is a property called as modulation property. So what does the modulation property tell? According to modulation property, x of t into cos omega naught t Fourier transform is, the most of the students have a doubt, shall I write pi times of this or 1 by 2 times? So it is 1 by 2 x of omega minus omega naught plus x of omega plus omega naught. This is called modulation property. There is another result like this, x of t into sin omega naught t, whose Fourier transform is like 1 by 2j. See, I am also getting confused. It is 1 by 2j x of omega minus omega naught minus x of omega plus omega naught. So let's put that formula here. This is called the modulation property, students. There are many properties like this. We will discuss one by one, and students have requested to solve some tricky questions from this topic. Definitely I'll solve them. So what are the other properties? Time shift, frequency shift, modulation. Let's go for time scaling. According to time scaling property, x of at Fourier transform is 1 by modulus of a x of omega by a. 1 by modulus of a. What does the time reversal property say? This is a very important one. What does the time reversal property say? X of minus t Fourier is x of minus omega. So we frequently say like this, if there is a compression in time, there is an expansion in the frequency, because here you see a into t and here you see omega by a. A reversal in time will lead to reversal in frequency. These are important ones. There is a big list, so let me go to the next page. So this is called duality or similarity property. So what does this say? According to duality or similarity, if one says that there is a time domain signal whose Fourier transform is x of omega, then capital X of t Fourier transform is 2 pi small x of minus omega. This creates a lot of confusion among the students. So this is a duality property for you. And there is the central ordinate property. So what does this say? Capital X of 0 value, this is very important. Capital X of 0 value is integral minus infinity to infinity. It is x of t dt. Or if you want area under x of t, if you want the value of this integral, then observe the Fourier transform at omega equal to 0. Similarly, small x of 0 value is 1 by 2 pi integration minus infinity to infinity. It is capital X of omega d omega. So this is called central ordinate property. There are many such properties. I am going to write them below. So please observe them. This is called differentiation in time. Which says d by dt of x of t Fourier transform is j omega x of omega. If you have a second derivative, then it is j omega whole square into x of omega. This is differentiation in time. So just like you have differentiation in time, there is something called differentiation in frequency. According to this, t x of t Fourier transform is j d by d omega of x of omega. T x of t Fourier transform is j d by d omega of x of omega. And then the most important one, which is called the convolution property. So let's see what happens. This is called convolution in time. X of t convolved with h of t, the Fourier transform is x of omega into h of omega. Just like convolution in time, we have multiplication in time. We put a tagline here. We say if you convolve in time and in the frequency you have multiplication. If you have multiplication in time, then the frequency domain there is a convolution. So multiplication in time. So what does this say? The Fourier transform of x of t into h of t is 1 by 2 pi. It is x of omega convolved with h of omega. So there is one more property which can be clubbed here, that's called integration in time. It's called integration in time. So what does this property says? Integral minus infinity to t x of tau d tau. You are not finding Fourier transform of x of t. You are integrating from minus infinity to t. You are getting a new signal and you are interested in Fourier transform of that. And the answer is, it is x of omega by j omega plus pi del of. So it's pi capital X of 0 into del of omega. These are some of the most important properties in Fourier transform. So this was the interesting problem. It's like a trap, you know. They'll frighten you with expressions like this. Question number 33 means it's a 1 mark problem. This is your electrical paper. I have never seen a function called e power minus t power 4 cos t. Some students, just by looking at that expression e power minus t power 4 cos t, they are gone. They say, I don't want to solve this problem. What are they asking? The value of the derivative of x of omega at omega equal to 0. Okay. First of all, what is x of omega? Integration minus infinity to infinity. It is x of t e power minus omega t dt. They are not asking you the value of x of omega. They are first saying calculate the derivative. Okay, I will find the derivative of x of omega. Integration minus infinity to infinity x of t. What's the derivative of e power minus j omega t, that too with respect to omega? It's minus jt e power minus j omega t dt. Now they want the derivative value at omega equal to 0. So you can now write at omega equal to 0, come on, d by d omega of x of omega value is, you can put minus j out, integral minus infinity to infinity, t is there because there is a t here, and what is x of t by the way? It's e power minus t power 4 cos t, and then e power in the place of omega, if you put 0, e power 0 is 1 and you are left with just dt. So this is the answer now. So you can see that this portion is the even signal and this is odd. This looks like a even signal into odd signal, giving you odd signal. Integrating an odd signal from minus infinity to infinity will give you the answer as 0. So the answer for this problem is 0, students. Solve this question, which is from sampling theorem, students. They say x of t is 2 cos 180 pi t cos 60 pi t is sampled at 200 Hz and it is passed through an ideal low pass filter having a cutoff frequency of 100 Hz. The maximum frequency present in the filtered signal in Hertz is dash. Firstly, why don't you write x of t like this? 2 cos a cos b is cos of a plus b. Cos of a plus b is like cos 240 pi plus cos of a minus b. 180 minus 180 pi minus 60 pi is 120. This is cos 120 pi. Students, everything is in Hertz. So what is the Fourier transform of this fellow? I would like to write the Fourier transform in f scale. 240 pi means divided by 2 pi, 120 Hertz. So the Fourier transform of this contains two impulses, one at minus 120 and other at 120. Which scale? This is Hertz scale. What is this? This is x of f. What's the Fourier transform of this? The frequency is 120 pi but in radians per second. I want to write in Hertz, so it is 60. There are two impulses, students, one at minus 60, other at 60. What is this? This is x of f. What next? Can you write the Fourier transform of the sampled signal? Can you write Fourier transform of the sampled signal? So what's the expression for the Fourier transform of the sampled signal? Of the sampled signal is like 1 by t summation n from minus infinity to infinity. It is x of omega minus n omega naught. They also gave the sampling frequency, students. What is the sampling frequency? It is 200 Hertz. If you can draw this expression, the problem is over. And while drawing that expression, I'll be drawing the spectrum of this. This whole spectrum is passed through a low pass filter whose cutoff frequency is 100. Anything beyond 100 you need not draw. That's the idea. Shall we draw it here? So let's draw it here itself. In a single page we will solve it. Most of you have already solved. I solved these questions or this kind of questions in the classroom. I said what things you have to remember. You have to remember the Fourier transform of the input signal. You have to remember the Fourier transform of the sampled signal. So see this, I am drawing the Fourier transform of the sampled signal. What you have to do is, first you have to draw the given spectra. Minus 120, minus 60, and then 120. Because this is related to n equal to 0, you have to draw the same spectra, and when you take n as 1, it is x of omega minus omega naught, x of omega minus omega naught. You have to shift this entire spectra towards right side by your sampling frequency. What is the sampling frequency? 200 Hertz. I will use another color where I am trying to shift this entire spectra towards right side by 200. What is minus 120 plus 200? 80. Where shall I draw 80? So this is where you have to draw 80. Next, minus 60 plus 200 is 140. Next, 60 plus 200 is 260. And then 120 plus 200 is 320. So if you have shifted this towards right, you should also shift towards the left, because here you have n equal to minus 1 as well. So whatever you have drawn, like impulse at 80, impulse at 140, 260, 320, draw the same thing to the left side. So minus 80. So you'll have an impulse at minus 80, minus 140, impulse at minus 260, and an impulse at minus 320. Actually, we can ignore all these fellows, ignore this, ignore this, ignore this, ignore this. You can ignore this, ignore this, ignore this, ignore this. Why? Because this spectra is now passed through a ideal low pass filter with cutoff frequency 100. Okay. I have expanded three terms, one is x of omega I have written x of omega minus omega naught, and I have also drawn x of omega plus omega naught. But there are many terms. Let's look at the other term. You can take n as 2. If you take n as 2, then it is x of omega minus 2 omega naught. You have to shift this entire spectra towards right side by 2 fs, that is 400. If you shift this towards right side by 400, what is minus 120 plus 400? Is it 280? Yes, 280, but I don't want to draw because there is ideal low pass filter which is anyway going to reject that. So this impulse itself is getting rejected. These are to the right side, they also get rejected. There is no need to draw anything because all other impulses which you draw will be rejected by the filter. So better what we do is we imagine one low pass filter. Let's imagine one low pass filter. This is a low pass filter whose cutoff frequency is 100. So whichever impulses are within this band, only they are seen at the output, remaining all are rejected by this filter. So what would be the output means? In the output you have an impulse at minus 80, minus 60, 60 and 80. Among this, what's the question? The maximum frequency present in the filtered signal in hertz. So what's the maximum frequency? The maximum frequency at the output of the filter is 80 hertz. 80 is the answer. So this happens because of aliasing. Now why aliasing took place? Why aliasing took place, I'll tell you. If you look at the input spectra, the maximum frequency is 120 hertz. When the maximum frequency is 120 hertz, you should have used at least 2 into 120, that is 240 hertz as your sampling frequency. But how much did you use? You used only 200 hertz. So this leads to aliasing. So many concepts are covered in this particular problem. This is the most expected thing in your upcoming GATE examination. When I say sampling theorem, so where did I write that sampling theorem? You must know what is the appropriate sampling rate. Your sampling rate must be at least 2 FM. And the minimum sampling frequency is called the Nyquist rate, which is 2 FM. And the Fourier transform of the sampled signal, this is important. These are the most important things from the Fourier transforms.